All right, this is a video to discuss some of the coding aspects that we did in class today. And I know there were a number of people that were absent due to IASIS, and I was out for one class, so I'm basically going to go over this a little bit. So what I've done is navigated to our trinket page. I'm looking at the section under rotational motion, introduction to torque and rotation. So we'll start off with this, and this is a scenario where we have a piece of wood that is, or a bar that is hinged here on a top of a building. And if I run it right now, it currently doesn't do anything yet because it doesn't, if you look at it, everything's perfectly in equilibrium. So the first question I ask you to do is you want to make it so that the bar is no longer under equilibrium, and you need to change the code to do that. So looking through the code here, you can see that there's the objects that I made, the building and the bar. And then the edge of it is defined in the hinge. And what we need to do, if you have not figured that out, is we need to kind of shift this bar a little bit over to the right. All right, so if I change this, I guess the bar, and make it a little bit to the right. Right now, half of it's on the right side and half it's on top of the building, so it's not going to be moving because it's perfectly in equilibrium. But if I change this to, say, a 3, for example, and then I run play, you'll see that the bar does rotate now, all right, for a period of time. All right, now, there is, if you look through here, a little bit of a calculation error. If you recall torque and how it's calculated. So I want you to take a look at this torque calculation and see what do you think is the mistake in here. And if you recall in the notes, maybe you want to go back to this video, example 14, we had a similar example where a bar rotates. And if you were to draw the forces that are acting on this, you have the force of gravity acting down here. Then you have the arm, which is here, R. And the torque is calculated by doing R times Fg times the sine of the angle that is between the arm, R, and the force. And so in this case, it would be R times mg times the sine of 90. However, as the bar starts to rotate, like in this picture, you'll see the force of gravity is still acting straight down, mg, and you have the arm that is acting along here, R, all right? However, the angle in here is no longer 90. So the problem, if you go back to our code, it lies with this line 24, our calculation for the torque. This is good at the beginning, right? When this bar here is essentially perpendicular, the arm is R and then Fg is straight down, so you got a 90-degree angle. But the problem is that as the bar starts to rotate, the angle is no longer 90 degrees. So you need to fix that. All right, so that's the major problem that's in this problem. It does rotate, it rotates at a constant angular acceleration. So what we need to do here to fix it is multiply by the sine of the angle of pi divided by 2 minus theta. Now you might be wondering, why do I have to do pi divided by 2? That's because the angle starts off to be 0, theta, all right, but it's actually really pi over 2. So as theta changes over time, the torque is going to be recalculated. Now, if I basically run this again, you're going to find that I still have an error, all right? Let me just scroll up here. I still have an error because the problem is within our code is that it does rotate, calculates it correctly, but it's not doing it within the loop. It calculates the torque outside of the loop, calculates the angular acceleration outside of the loop, and then it sets the same acceleration all the way through. So really, what we need to do is we need to take this line 24, all right, and add it in within our loop, all right, because every time it goes through the loop, it needs to update the angle, and then also update the angular acceleration, alpha. So we'll just add that in here, and now it should be calculating it correctly. So if I run it, now it may look kind of similar, but it actually, if you notice that the angular acceleration is a maximum at the beginning, and it actually, by the time it becomes vertical, By the way, right now this angle, like it stops at 1. Maybe I could do like 1.5 or something like that. And maybe you'll see it rotate a little bit longer. So essentially what should happen is it's accelerating largely at the beginning, and then it actually doesn't accelerate as much. In fact, when it's completely vertical, this bar, then there is no acceleration. Okay, some other aspects that you should probably look at is how do we make this bar rotate? These lines in here. All right, and that's what we're going to kind of focus on in the next little bit, is how do we make something rotate and change the angle over time. And we're using the Euler method, Euler-Kromer method here. So there are some other aspects in here, but I'm going to skip that for the essence of time. And I'll just briefly introduce these lines 31 and 32 a little bit and just talk about how this works. Perhaps I go to try to show you what's happening here. So we're going to go back to over here, and maybe I'll just use this white space so I can write on here. So what we're doing here is, if you recall the Euler-Kromer method, we are, let's say I have, let's do it just with linear motion. If you have acceleration versus time graph, and let's say, just to keep it simple, is we have an acceleration that's nice and constant over time. And if you take a little chunk of time in here, we'll call that delta t, and then you multiply the magnitude of the acceleration by that little chunk of time delta t, you hopefully recall that the area under an acceleration time graph, so a times that little chunk of delta t, will give you a change in velocity. All right, so that little chunk of area represents a change in velocity. So then let's say that you know the velocity at some particular point, like right up to here, and you want to know what the next velocity is going to be. So you can find the new velocity by taking the old velocity and adding the change in velocity that occurred. All right, so let's say I know what that change velocity is, so I can really say that the new velocity is the old velocity that I had over here, and then I'm going to add in this chunk of velocity that changed by, and which will be a times dt. This is basically the Euler-Kromer method. So let's say the velocity here was like 1, and then I had a little extra velocity of, say, 0.1. So now the new velocity will be a little bit more and be 1.1. And you can basically, through each time step, you calculate that. Now, of course, now that you know what the new velocity is, then you can find its position. So let's say I want to find the position of it. Well, then I use the velocity time graph, and I can calculate the area under that. Now, to make things a little bit simpler, we don't use a trapezoid. We basically are going to assume that this is a rectangle, and we're just going to do the area of that rectangle. So the area under a velocity time graph, so in this case would be v multiplied by the width of that rectangle, which would be dt. That area gives you v times delta t, which gives you basically a displacement. So how do we find its new position? Let's say the position is like here, and I want to find my new position afterwards. My new position will be equal to my old position plus that chunk of displacement, that change in displacement, so that delta x. So it'll be the old displacement plus basically v times delta t. So how does this all work out in code? So we don't use delta t, we call dt. So basically delta v is equal to a times dt. So that's the key thing you need to remember. And then, well, delta x would be equal to v times dt. And that would tell you the change in x. So if in code to write this line, you would just write v equals v plus basically a times dt. So this line in code is written this way. All right, and then this line in code over here, you could write as x equals x plus basically v times dt. And that's that line in code over there. Okay, so we're now, that was the way we did it before when we did things that moved in a linear way, right? But we're now doing things that are moving in an angular way. So how do we modify all this? Well, it's just simple little changes. Let's change this to an acceleration, alpha, an angular acceleration. So instead of being a in here, we do alpha times dt. All right, and then instead of linear velocity, we're going to do angular velocity. So now instead of v's, they will be w or omega equals omega plus alpha times dt. All right, and then instead of x, this is going to be theta. So x will be theta equals theta plus omega times dt. Okay, now in code, we just write the word theta instead of writing the symbol theta. And then we just use W for omega. Okay, so that's the key. If we go back to our code, all right, where is it? Over here. This is what's happening. Here, I'm updating the velocity. So maybe I'll just add a little comment in here. I am essentially updating the angular velocity. And in here, I am updating the rotated angle. And those two lines are very key in understanding what's going on. And then the last line you probably know, this is just updating the time. Okay. Now, if you recall, by the way, omega plus equals is a short way in Python to write essentially omega equals omega plus alpha dt. Okay. And again, here you could write alpha, theta equals theta plus omega t times dt. Okay. I think this video has gone on a little bit long. So the next part we're going to do in my next video is we're going to switch over here and we're going to go to compounding objects and rotating objects. So I'll stop here. You go to the next video and we're going to look at how we can rotate objects. There are two methods.